Okay, so before we resume our discussion on diff amp, let me just clarify or just go through the following so that everyone is comfortable. So let's say you have an NMOS transistor like this. Gate is incrementally short, source is incrementally short. What is the resistance looking here? It is R0 of the transistor. Okay, VGS is short, so GM VGS disappears, only R0 remains. So again, this I have drawn only for the small signal. So in the actual circuit, the gate will be connected to some DC bias voltage, so will be the source. Okay. Now similarly, if you have a PMOS whose gate is incrementally short, source is incrementally short, what is the looking in resistance? It is still why 1 by GM? I mean, looking, remember that for a PMOS, again the gate is short, source is short. So in small signal, GM VGS, will it be there or will it not be there? So what is the only thing remaining? Again, this again says that with respect to small signals, there is no difference in using an NMOS or a PMOS transistor. Okay. So now let's say you have this scenario wherein the drain is incrementally short, gate is incrementally short. So what is the resistance looking into the source now? 1 by? Yeah, it is 1 by GM. Ideally, exactly it's 1 by GM in parallel with R0 because the R0 of the transistor is also appearing here, but for all practical purposes, this is approximately 1 by GM. Assuming the transistor is in saturation, this can be ignored. So now let's say you have this setup, you have a resistor RD and gate is again incrementally short. So here what is the looking in resistance? This was something I asked you to work out. Does anyone remember the result? Yeah, it turns out to be this expression. And when can I approximate this to be 1 by GM? At least from this expression, it's not just GM R0 greater than 1. Should have RD to be smaller compared to R0. Then you can basically ignore this part and you will get only this term that becomes 1 by GM. So this is true if RD is much smaller than R0. Again, the limiting case is what we saw in the first lecture. If RD is infinite, then this is open circuit. If this is open circuit, what is the resistance looking in? Infinite. Okay, so then let us say you have this setup, drain is incrementally short, gate is short, you have a resistor RS, sorry, drain is not short, let's say. So what is the resistance looking here now? What is the resistance looking into the drain now? What configuration does it remind you of? Cascode. So again the output resistance is the resistance you have at the bottom, which is RS, plus the output resistance of the cascode transistor, which is R0, plus the intrinsic gain of the cascode transistor times whatever resistance you have at the bottom. So that is GM R0 times RS. Okay. So one last thing. So then let's say you have this drain is incrementally short. Here you apply a small signal Vi and I have RS. What is the small signal V out here? Let's say you don't consider R0 for simplicity. What is V out in terms of Vi? How much was this? Okay, again you try to find, right, what is the short circuit GM here? If a short circuit is, what is the short circuit GM? GM. What is the looking in resistance? Here, looking down, what is the resistance you have? RS. Looking up, what do you have? 1 by GM. So this should be GM into RS parallel 1 by GM. So this should turn out to be GM RS by. So, I mean, please make sure you understand this and are fluent with this. We will be using multiple times throughout the course. And I gave a lot more problems in the practice set. So, please work out and make sure you are comfortable. Again, ideal scenario will be for you to just look at those circuits and by inspection give the final result, because most of that are single transistor or two transistor circuits. But of course, for all circuit you might not be able to do it. So, as I mentioned, you work out using small signal analysis what result you get. But don't stop there, you try to make sense of the result, right? Like how we did in the class. 10 GM to 0 infinity, resistance to 0 infinity, and try to see why that makes sense. And that's how we build intuition. Okay. So remember, as I mentioned in the first class, just doing an exact analysis is good, but that's just the bare minimum. If you want to be a valuable designer, it is this kind of intuition that you should develop. Okay, great. Then let's move on. So we have been looking at the diff amp. So if I were to recap, we started off with this configuration. Oops, what happened? Here we wanted to buffer V2, so used an ideal buffer. So then this voltage was V2 and the gain was GM times RD. Then we replaced this buffer with a common drain configuration. So this was non-ideal because the output resistance was not 0. And also, just like how V2 was affecting this voltage, V1 will also affect this voltage. So this is something we calculated in the last class, and we found that the gain was GM RD by 2. So the point to notice, if we had an ideal buffer, the gain was GM RD. But when I make this diff amp configuration finally, the gain is reduced by a factor of 2, right? And also we remark that for symmetric circuits like this, we can analyze it using the common mode and differential mode half circuits. So here again we calculated the gain to be the same, GM times the resistance RD in parallel to the R0 of the transistor by 2, right? Then we wanted to increase the gain, so we decided to increase RD. So we replaced by a current source, and this current source was realized using a PMOS transistor. So what is the resistance looking into the drain of the PMOS transistor? What is the small signal resistance here? R0 of the PMOS transistor. So in our earlier analysis, whatever we had, RD is essentially replaced by R0 of the PMOS transistor. So the result should be GM times R0 of the PMOS transistor in parallel to the R0 of the NMOS transistor by 2. Okay. So that's what we got. Yeah, so GM times, yeah, here I made I forgot to include a factor of 2. So please pay attention. If I make any mistakes like this, just call me out immediately. So here it is GM times R0 of the PMOS parallel with R0 of NMOS by 2. But then we saw that this bias voltage we can generate it in the same branch, so that gave rise to this guy. So here we first calculated the DC operating point. So a couple of points to note here are, although this circuit is asymmetric, as long as we provide a common mode excitation wherein both sides are excited by the same inputs, then this becomes symmetric. Then the currents in both branches are equal, and so will be the two drain voltages, right? And another point we noted was, if I increase the bias voltage VB, do you think the currents in the transistor change? No. But what changes to keep the bias current constant? Yeah, this common source voltage Vx changes automatically to keep the current constant. So then we found the short circuit GM and R out for this. So the short circuit GM was short circuit GM was essentially GM of the NMOS transistor, should not be surprising, and the output resistance was R0 of NMOS parallel to the R0 of PMOS approximately. But this doesn't necessarily mean that looking up you have R0 of the NMOS transistor, and looking down it is looking up it is R0 of PMOS, and looking down it is R0 of NMOS. In fact, looking down, the resistance was 2 times the R0 of the NMOS transistor. But luckily all the planets and the stars align in such a way that at the end of the day things work out to be a nice simple expression like this. It's a nice way to remember, but note that it is not as though looking down it is R0 N. So the overall gain of this circuit was GM times R0 of the NMOS in parallel to R0 of the PMOS. And as we see, compared to this earlier circuit, the gain is basically increased by a factor of 2. And that should not be surprising, because in the earlier diff amp we had small signal currents flowing in both the branches, but we only tap the output from the right side branch, which means we are not making use of the small signal current flowing in the left side branch, right? Whereas if I look at this circuit, the small signal current flowing in the left branch is mirrored using this PMOS transistor and then added to the output. So this way we are not wasting any small signal current, we are utilizing everything, and that can be apparent if I look at the small signal short circuit GM calculation. So as we saw, we have small signal currents in both branches. So this current obviously adds to the output, but even this current is mirrored by this PMOS current mirror, and that kind of contributes to it. So the short circuit GM you get is GM, whereas in the earlier diff amp circuit, where did it go? Sorry? Yeah, in the earlier diff amp circuit, if you try to find the short circuit GM, you will find it to be GM by 2. That would be the difference. Okay. Great. So let me now copy this. So here the gain, let me write it again, it is GM of the NMOS times R0 of the NMOS in parallel to R0 of the PMOS transistor. Okay. Great. So now we seem to have a candidate for making an opamp, and remember the opamp is essentially this fellow. And what kind of control source is an ideal opamp? Voltage control? Voltage. Voltage control, voltage source. So if let us say this is V1, V2, the gain is A, the output voltage will be, let me write it here. So V out will essentially be A times V1 minus V2, right? So if I go and add a resistor RL at the output, what will happen to the output voltage? Will it change or will it not change? It will not change. So why will it not change? Yeah, it's a voltage controlled voltage source. So it doesn't matter what resistor is connected across the voltage source, the voltage is constant. So let's say now I try to connect RL here. And by the way, can I connect the RL directly from here to ground? Is it fine if I make this connection? No. Why not? Yeah, she's saying, remember I'll essentially add some biasing here and then apply small signal, right? And with respect to DC operating point, what do you want the currents in the transistors to be? I0 by 2. Now if I take a resistor and connect it to ground, this will steal a current. So bias point will be screwed up. So what do you do in general? You add a capacitor, and what should be the value of the capacitor ideally? Should be infinitely large, right? But it turns out on chip this is not a great thing to do, because as you know, larger capacitor means larger area. I mean epsilon times area by D is the capacitance. So we generally don't want to do this. Okay. So which means what should change here so that I can connect the resistor directly but prevent any DC current flowing here? That is, what can I change here so that no DC current flows through the resistor? No, load is not under your control. There is a load. There are two things. RL is fixed and I want to make sure I want to connect this terminal here. So what else can I change here so that no current flows? Okay, first of all, okay. Why is the current flowing here? Sorry? Okay, there is a potential difference between these two current flows. If I don't want to have any current flow, what do you do? Yeah, so instead of connecting it to ground, what should I connect it to? If I connect it back to here, there is nothing, right? So ideally I should connect it to some DC voltage. Yeah, and that voltage should be equal to the operating point voltage of these two. Fine. So that's what you typically do. Let's say call it some V out DC. So that's what we typically do. You try to connect it to an appropriate voltage so that no DC current flows, right? So anyways, now let us say you connect RL appropriately using capacitor or something like this. But what will happen to the small signal gain now? With respect to small signal, it is connected to ground. So what will happen to the small signal gain now? So this will come in. This clear? RL just comes in parallel to what you have at the output. So do you think now the output voltage will change with respect to RL, or will it not change? It will change, right? Yeah, but remember, an ideal voltage control voltage source should not behave that way. So which means what we have designed is not truly a voltage controlled voltage source. Turns out this guy is a voltage controlled current source. Okay. So instead of making an operational amplifier, what we have at our hand is an operational transconductance amplifier. But RL is not under your control, right? I mean, like he's saying, if RL is really large, it's not a problem. The real problem comes when RL is smaller in comparison to your existing output resistance. Okay.
So in the small signal model, we are operating with a higher frequency so that the lower capacitance value is also accepted.
Yeah, still you need to have a capacitance, right? Now let's say you're trying at very low frequencies, right? It is not like always you operate at high frequencies, right? There are a lot of sensor applications, biomedical applications where the frequency is like less than 100 Hertz. So then the capacitance required will be really large. Yeah, but like you mentioned, if your operating frequency is large, you can have a reasonably sized capacitance. I'm not saying this is not at all done. This can be done, but in general you try to avoid capacitance. Yeah, so we have an OTA, and the symbol for the OTA is a quadrilateral instead of a triangle now. So this is V1, V2. So just like how here the output voltage was fixed in a VCVS, in a VCCS, what is fixed, do you think? Output current will be fixed. Okay. And this will be equal to a proportionality constant GM times V1 minus V2. And you have its own intrinsic R out, like this.
In this, you said it's not a voltage source.
Correct.
But sir, it is not even a current source because it will change with respect to RL.
Yeah, it is not. I mean, I would say, okay, it's a good question. So now tell me, for an ideal voltage source, what should be the output resistance or the series resistance? For an ideal voltage source, what should be the series output resistance? 0 or really small. For a good current source, what should be the or very large? Here the output resistance is small or large? You want it to be large, right? So this actually behaves like a better current source.
Can you say it like this? Every element is a voltage controlled current source.
Yeah, exactly. I mean, that's what I was getting at. This shouldn't be surprising because we are making this entire thing using transistors. And as you know, transistors are voltage controlled current source. So it's not surprising that the entire thing is also a VCCs. Okay, so now let us say I give you this block. Okay, so which means this is a black box. I give it to you. These are the terminals accessible to you. Okay, the input and the output, right? So how do you think you can measure this GM? Yeah, so you're saying if I short the output here, what will be the current flowing through the output? This current will be GM times V1 minus V2, but the point is you can't measure this current, so you short circuit the output, so all the current flows here. So that way you can measure what is your GM. And even that's how we have been calculating our gain also. You find the short circuit GM and R out, and that's exactly this. Fine. Okay, so then let me ask you this. So let us say this is the circuit you have. Okay, so here you are interested to find the short circuit GM. So what do? You try to go and connect this to ground. If I go and connect it to ground, do you think this will work? Why not? Again, bias point is completely messed up, because remember I am always giving a bias voltage and on top of it I apply small signals. So to measure the short circuit GM or the short circuit current, I should not be connecting it to actual ground. This should be, yeah, so small signal ground, AC ground. So what should I connect this to finally? Some voltage source. And what voltage source do you think I can connect here? So whatever the DC operating point voltage was, I'll connect the same voltage there. Okay. So that way I don't disrupt the DC operating point. That is, even if I don't connect the voltage source, this would have been at some DC operating point voltage. You go and put a voltage source of the same value, so nothing changes. But what we have established is, you have established a short circuit path with respect to small signals, which is what you want. Okay. So this is how you kind of measure whatever short circuit GM or short circuit current. Because remember, when I say GM, R out, etc., they are all small signal parameters. So when I say it is ground, it is a small signal ground or an AC ground. So in reality, this will be some DC voltage. Okay, great. Yeah, so let me now remark this. So this is typically called the 5 transistor OTA. Again, we have 4 transistors. The 5th transistor is this current source. So let me label the transistors, say M0, M1, M2, M3, M4. Great. So this is typically called the single stage OTA, because loosely speaking you have amplification coming from one stage. So do you think this will be a good candidate if I have a resistive load? If I have a resistive load, do you think this is a good candidate to use? Huh? I mean, assuming that you don't connect the resistor so that it disturbs the DC operating point. Let's say you put a large capacitor or connect the resistors other end to a DC voltage source appropriately. But as we saw, even if you have an RL here, it affects the small signal gain. So it is not a great choice for resistive loads, right? Only if your resistance is really large compared to your existing output resistance, this works. Otherwise, it is not great. So then, what kind of loads do you think this can be good? Huh? A capacitive load. Right? A capacitor doesn't change the DC gain. So that way it is good. So it's typically preferred if you have to drive capacitive loads.
So when adding a resistive load, the gain is increasing.
No, right? It's GM times you already have some existing R out. So your RL is coming in parallel to this, right? Anytime you put 2 resistors in parallel, yeah. Okay, great.